The universe has always been a realm of astonishing phenomena, but few objects manage to shake the very foundations of physics like LED 568. Unlike ordinary black holes, which behave predictably according to Einstein's equations and the well-established laws of gravity, this enigmatic object seems to defy every expectation. It emits signals that shouldn't exist, warps space and time in ways that seem impossible, and radiates energy patterns that leave astronomers questioning everything they thought they knew about the cosmos. LED 568 isn't just another black hole. It's a cosmic puzzle that could rewrite the rules of physics entirely, hinting at mysteries hidden deep within the universe that we've yet to comprehend. Its discovery forces a profound question. If one black hole can challenge the laws that govern reality, how many more could be lurking unseen, bending the universe to their will in ways we cannot yet imagine? What is LED 568? LED 568 is classified as a black hole, yet it quickly became apparent that it is unlike any black hole astronomers have studied before. Black holes, in general, are regions of space-time where gravity is so strong that nothing, not even light, can escape, defined by their event horizon. LED 568 was initially detected during a comprehensive deep space survey aimed at cataloguing extreme cosmic objects, using a combination of X-ray, gamma-ray, and radio telescopes. Its unusual emissions immediately drew attention because they did not match the standard energy patterns observed from black holes of similar mass and type. What sets LED 568 apart is not just the fact that it exists, it's the way it behaves. Astronomers noticed anomalies in its gravitational influence, energy output, and radiation patterns that defied expectations. Unlike ordinary black holes, which typically conform to predictable models based on mass and spin, LED 568 seemed to be operating outside the normal rules. Its discovery raised fundamental questions about whether our current understanding of black holes and the physical laws that describe them was complete. Scientists are paying close attention to LED 568 because it represents a unique opportunity to test the limits of physics. If confirmed, its irregularities could challenge decades of established theory in both general relativity and quantum mechanics. Researchers hope that studying LED 568 in detail could provide insights into phenomena previously thought to be theoretical, such as exotic matter, unusual space-time structures, or even potential connections to dark energy. Its importance lies not only in its strangeness, but in the fact that it forces a confrontation with the unknown, making it a high-priority target for observation with the latest generation of telescopes and space observatories. The laws black holes should follow. To understand why LED 568 is so perplexing, it helps to first review the standard laws that govern black holes, which have been remarkably consistent across decades of observation and theory. At the core of these laws is the event horizon, the boundary surrounding a black hole beyond which nothing can escape, not matter, not light, not even radiation. Once an object crosses this invisible threshold, it is irretrievably drawn inward, making the event horizon a one-way gate dictated by gravity. This fundamental principle forms the basis of how black holes interact with their surroundings and has been repeatedly confirmed in both astrophysical observations and theoretical models. Inside the event horizon lies the singularity, a point where all the matter that falls in is compressed into an infinitely small volume. At this singularity, density and gravitational forces theoretically become infinite, and the known laws of physics break down. While this concept is mathematically predicted by Einstein's general relativity, it remains largely theoretical, as no direct observation of a singularity is possible. Yet, the singularity is crucial because it represents the ultimate consequence of a black hole's gravitational dominance, a region where space and time themselves are warped beyond recognition. Outside the event horizon, black holes still exert extreme influence on their environment. Gravity dominates everything nearby, pulling in gas, dust, and even entire stars over time. This gravitational pull also affects the path of light, bending it in a phenomenon known as gravitational lensing, which has allowed astronomers to indirectly study black holes for decades. Additionally, matter spiraling toward a black hole typically forms an accretion disk, heating up and emitting X-rays and other forms of radiation in a manner consistent with established physical laws. In summary, the standard model of black holes relies on predictability, an event horizon that traps everything, a singularity where densities reach infinity, and a gravitational dominance that dictates the behavior of surrounding matter and light. These laws form the framework by which black holes are understood, and any deviation from them, such as what is observed with LID 568, signals a profound challenge to our comprehension of the cosmos. Where it lives. LID 568 resides in a remote corner of the universe, millions of light years away from Earth, making it impossible to study without the most advanced astronomical instruments. Current estimates place it in a dense, dynamic region of space that is home to several other extreme cosmic objects, including massive stars and clusters of smaller black holes. This neighborhood is far from the relative calm of our own Milky Way, immersed in turbulent interstellar gas clouds and energetic radiation fields that can obscure observations and make precise measurements challenging. Its exact location in terms of galactic coordinates remains a topic of ongoing research. But what is clear is that LID 568 exists in a part of the cosmos where the environment is both chaotic and highly energetic, a setting that may help explain some of its bizarre behavior. Unlike black holes nestled at the centers of galaxies, which often dominate their surroundings, LID 568 seems to occupy a more isolated position, far from the gravitational pull of a galactic nucleus. This isolation provides a unique advantage for astronomers. Its activity is less influenced by the nearby mass of stars or gas, meaning the anomalies we detect are likely intrinsic to the black hole itself rather than a product of its environment. At the same time, the sheer distance, tens or even hundreds of millions of light years, means that the signals we observe today actually left LID 568 millions of years ago, giving us a glimpse into its ancient past as well as its current oddities. Understanding where LID 568 lives is essential not just for mapping its position in the universe, but also for interpreting the unusual phenomena it produces. The combination of a turbulent, high-energy region with relative isolation may be a key factor in the black hole's defiance of normal physical laws, offering clues about the extreme conditions under which such anomalies can arise. In this sense, location is more than a point on a map. It is a window into the cosmic forces that might allow LID 568 to behave in ways no other black hole has been observed to do. Strange behavior detected. The first hints that LID 568 was anything but ordinary came from careful observation of its emissions and gravitational effects. When astronomers initially targeted the region, they expected to find the familiar signals associated with black holes: X-ray bursts from the accretion disk, predictable gravitational lensing, and standard relativistic jets. Instead, the data revealed anomalies that could not be reconciled with the known behavior of stellar mass or supermassive black holes. Radiation patterns fluctuated in unexpected ways, and the energy outputs sometimes spiked or dimmed without apparent cause. These irregularities immediately signaled that LID 568 was not following the rules of black holes as defined by decades of astrophysical research. One of the most striking observations was related to its accretion disk. In typical black holes, matter spiraling inward heats up and emits a consistent spectrum of X-rays. LID 568, however, displayed emissions that were unusually energetic and irregular, with bursts of radiation that seemed to defy the expected physical mechanisms. The timing and intensity of these emissions did not match the mass estimates of the black hole, leaving astronomers scratching their heads. In addition, gravitational effects on nearby objects appeared to fluctuate, as if the strength of LID 568's pull was not uniform over time, further hinting at a breakdown of standard gravitational behavior. These early signs of strange behavior were not minor deviations. They were fundamental contradictions to the predictions of general relativity and the standard black hole model. The black hole's unusual emissions, energy variations, and gravitational inconsistencies suggested that something entirely unknown was influencing its behavior. For scientists, these anomalies represented more than a curiosity. They were a call to explore the limits of physics itself, forcing a reconsideration of concepts once thought inviolable. Lead 568 had made it clear. This was no ordinary black hole, and whatever was causing these strange readings could challenge the very foundation of our understanding of the universe. Breaking gravity's rules. One of the most confounding aspects of Lead 568 is how it seems to defy the very laws of gravity that define our understanding of the cosmos. Gravity, according to Einstein's general relativity, is a manifestation of space-time curvature caused by mass and energy. In a standard black hole, this means that the closer you approach the event horizon, the more intense the gravitational pull becomes, reaching theoretically infinite strength at the singularity. This predictable relationship has been verified across countless observations, from the behavior of stars orbiting the supermassive black hole at the center of the Milky Way to the bending of light around massive galaxy clusters. However, LID 568 refuses to obey these established rules. Measurements of its gravitational influence on nearby stars and gas clouds reveal anomalies that cannot be explained by conventional models. In some regions around LID 568, objects appear to accelerate as though experiencing stronger gravity than would be expected given the black hole's estimated mass. Yet in other regions, objects orbit at speeds that are inexplicably slower, almost as if the gravitational field is unevenly distributed in ways that violate the symmetry predicted by general relativity. These inconsistencies have prompted astronomers to re-examine their assumptions, including the mass estimates and the distribution of matter around the black hole. Yet even after accounting for surrounding matter, dark matter contributions, and observational uncertainties, the anomalies persist. Even more perplexing is the apparent stretching of space-time in Lead 568's vicinity, which does not conform to the classic Schwarzschild or Kerr metrics used to describe black holes. In standard models, the geometry of space-time near a non-rotating black hole forms a spherically symmetric well, and near a rotating black hole, it produces the familiar frame-dragging effects, where space-time itself is twisted around the rotating mass. LID 568, however, shows signs that space-time may be warped in irregular, unpredictable ways, suggesting that its internal structure, or the physics governing it, is fundamentally different from anything previously observed. Some calculations indicate that if general relativity were strictly applied to LID 568, the black hole's observed gravitational pull should cause nearby objects to move in entirely different trajectories. Yet reality does not match this prediction. This discrepancy is particularly significant because general relativity is the foundation upon which modern astrophysics is built. To see a black hole apparently defying these equations is equivalent to watching a planetary orbit violate Kepler's laws, something so unprecedented that it shakes the foundations of theoretical physics. One line of inquiry focuses on whether LID 568 could be interacting with unknown forms of matter or energy, such as exotic matter with negative mass, which could produce gravitational effects that mimic violations of general relativity. Another hypothesis is that the black hole might not be a true singularity in the conventional sense, but instead a more complex structure, perhaps a bridge in space-time or a wormhole, which could distort gravity in ways that standard equations do not account for. Astronomers have also considered the possibility of higher dimensional effects. In theories such as string theory or brane-world cosmologies, gravity could leak into or from extra-spatial dimensions, subtly altering the gravitational field that we observe in our three-dimensional space. LID 568 might be a rare window into these hidden dimensions, where gravity behaves not according to four-dimensional general relativity, but according to a more complex, multi-dimensional framework. If true, observing LID 568's effects could provide the first direct evidence of higher dimensions, something physicists have long speculated about but never empirically detected. Another angle of investigation is quantum gravity, the elusive theory that seeks to reconcile general relativity with quantum mechanics. Near the singularity of a black hole, classical general relativity predicts infinite density and curvature, but quantum mechanics imposes limits on how matter and energy behave on extremely small scales. LID 568 may represent a regime where these two frameworks clash in observable ways, creating gravitational effects that seem to break known laws. Some theorists speculate that quantum fluctuations in space-time, amplified near this black hole, could produce the irregular gravitational fields we detect, essentially making LID 568 a natural laboratory for quantum gravity research. In addition to the theoretical puzzles, LID 568's gravitational anomalies are measurable through the movement of nearby stars and interstellar gas. Astronomers have tracked stellar orbits using high-resolution telescopes over multiple years, expecting them to follow predictable paths dictated by Newtonian approximations and relativistic corrections. Instead, some stars exhibit unexpected accelerations or decelerations, while gas clouds are stretched or compressed in unusual ways, inconsistent with a smooth gravitational gradient. These observations are precise enough that they cannot be dismissed as errors, compelling scientists to accept that the gravitational rules around LID 568 are indeed breaking down, or at least behaving in ways that our current equations cannot model. Even light behaves oddly near this black hole. According to Einstein, light should bend predictably in the gravitational well, producing phenomena like gravitational lensing. LID 568, however, exhibits lensing effects that are sometimes stronger or weaker than predicted, and in some observations, light appears to curve in ways that suggest the gravitational field is asymmetric or fluctuating over time. These deviations are subtle but consistent, adding another layer to the mystery and making it clear that this black hole cannot be fully described by classical theory alone. The stakes of this discovery go far beyond curiosity. If LID 568 truly breaks gravity's rules, it forces us to confront the possibility that our understanding of space-time, mass, and energy is incomplete. It raises questions about the universality of general relativity and whether other black holes might also harbor anomalies that we have simply not yet detected. The idea that a single black hole millions of light years away could expose cracks in one of physics' most successful theories is as exhilarating as it is unsettling. It also underscores the importance of future observations and more sophisticated models that can accommodate deviations from classical expectations, whether through higher dimensional theories, exotic matter, or yet to be discovered physics. Ultimately, LID 568 is challenging the very concept of gravity as a fixed and universal force. Its unpredictable pull, uneven space-time warping, and anomalous effects on light and matter suggest that a deeper layer of reality is at play, one that may require new mathematics, novel theories, or an entirely different understanding of the fabric of the universe. As observations continue and simulations improve, scientists hope to either reconcile LID 568's behavior with an extended framework of physics or embrace the revolutionary conclusion that our current models are insufficient. Either outcome would have profound implications, potentially opening the door to a new era in cosmology where black holes are not merely points of no return, but windows into physics beyond the limits of human knowledge. Light that shouldn't escape. One of the most bewildering phenomena observed around LID 568 is the presence of light and other forms of electromagnetic radiation appearing to escape from regions where, according to conventional physics, nothing should be able to break free. In the standard black hole model, the event horizon is an absolute boundary. Once matter or radiation crosses it, escape is impossible, trapped forever by the black hole's immense gravitational pull. Yet ELID 568 has consistently demonstrated signals that seem to violate this fundamental principle. Astronomers have detected bursts of X-rays, gamma rays, and even visible light that appear to originate perilously close to, or perhaps even from within, the event horizon itself. This defies the expectation that no information or energy should be able to escape from beyond that boundary. The emissions themselves are highly unusual. For example, telescopic data indicate sporadic, high-intensity X-ray flashes that do not match the steady output typically produced by a black hole's accretion disk. Unlike normal black holes, where the radiation from the disk follows predictable patterns dictated by gravitational compression and frictional heating, LID 568 produces bursts that are irregular in both timing and intensity. Some of these flashes are so energetic that if they were truly coming from inside the event horizon, they would require mechanisms entirely unknown to current physics. Even more puzzling is that some of the detected emissions show a polarization and energy spectrum that suggest they are not simply being deflected from the outer regions, but might be originating from deep within the gravitational trap. Adding to the mystery are reports of unusual relativistic jets. Black holes often produce jets of charged particles that shoot out along their rotational axis at near light speeds, powered by magnetic fields in the accretion disk. However, the jets associated with LID 568 are inconsistent with any known models. They sometimes appear to emerge from angles that do not align with the black hole's rotation, or from regions closer to the event horizon than theory predicts. In certain observations, radiation appears to leak along unexpected trajectories, as if the black hole's gravitational grip is weaker in localized regions, or as if some mechanism is allowing energy to tunnel through the event horizon. Some scientists have suggested that quantum effects could be responsible for these anomalies. Theoretical models like Hawking radiation predict that black holes can emit particles due to quantum fluctuations near the event horizon, but the scale of emissions from LID 568 is orders of magnitude larger than Hawking radiation would allow. These emissions are not mere whispers of energy. They are significant, measurable bursts that could indicate either a new form of radiation or a completely unknown physical process. If confirmed, this would force a radical rethinking of what the event horizon actually represents and whether it is truly an absolute boundary. There are also hypotheses involving exotic physics, such as the presence of matter with negative energy, or even micro-wormholes embedded within the black hole, which could allow energy to escape in ways that mimic violations of the event horizon. Another idea posits that LID 568 might be connected to higher dimensional structures or parallel regions of spacetime, permitting light and energy to leak through shortcuts inaccessible to ordinary three-dimensional space. While these ideas may sound speculative, the observational data leave few alternatives. Either there is some unknown mechanism within the black hole enabling these emissions, or our fundamental understanding of the event horizon and gravitational constraints is incomplete. The implications of light escaping from what should be an inescapable boundary are profound. It challenges one of the core tenets of both general relativity and quantum mechanics, that information and energy cannot exit a black hole once past the event horizon. If LID 568 is indeed allowing such escape, it raises questions about the fate of information in black holes, the limits of causality, and the fundamental structure of space-time. Moreover, it could provide a unique observational window into the interior dynamics of a black hole, a region that has historically been considered unobservable and unknowable. The unusual emissions from LID 568 have sparked intense debate in the astrophysical community. Researchers are exploring every potential explanation, from measurement errors to novel astrophysical processes, but so far, none can fully account for the data. Each new observation reinforces the notion that this black hole is unlike any other, and that it may represent a glimpse into physics beyond our current theories. Whether through exotic matter, quantum tunneling, or previously unimagined space-time geometries, LID 568 appears to be breaking one of the most fundamental rules of the universe, that once something crosses a black hole's event horizon, it can never return. In essence, the light and radiation that seem to escape LID 568 are more than mere anomalies. They are signposts pointing toward gaps in our understanding of the cosmos. They challenge the very definition of what a black hole is, suggesting that the event horizon may not be an absolute boundary after all, or that under certain extreme conditions, nature finds a loophole in its own laws. The study of these emissions is ongoing, and as more powerful telescopes and observational techniques are applied, scientists hope to uncover whether LID 568 is a singular cosmic anomaly or the first of many black holes that behave in ways previously thought impossible. Energy output. Mystery. Another layer of LID 568's enigma lies in its energy output, which defies every prediction astronomers have made based on black hole physics. Typically, a black hole's energy emissions are largely determined by the behavior of matter in its accretion disk. Gas, dust, and other material spiral toward the event horizon, heating up to millions of degrees and releasing energy primarily as X-rays. The intensity, frequency, and distribution of these emissions can be modeled with remarkable accuracy, allowing scientists to estimate a black hole's mass, spin, and surrounding environment. LID 568, however, refuses to conform to these expectations. Its observed energy output is irregular, unpredictable, and in some cases, dramatically higher than standard models would allow. Detailed measurements show that LID 568 exhibits fluctuations in luminosity that occur on timescales too short to align with the size and mass of the black hole. In a typical stellar mass or supermassive black hole, the time it takes for matter to travel from the outer accretion disk to the event horizon sets a natural rhythm for energy emission. But LID 568 produces bursts of energy that appear to originate from regions so close to the event horizon that, under conventional physics, the matter would have no time to accelerate and radiate in such a pattern. These bursts are not just sporadic. They sometimes exceed the total energy output expected for a black hole of comparable mass by significant margins, suggesting either a fundamentally new mechanism of energy production or a breakdown in our understanding of gravitational physics. In addition to excessive output, the energy distribution itself is puzzling. Observations across the electromagnetic spectrum, from radio waves to gamma rays, indicate patterns that do not match any known accretion disk models. Typically, the hottest, most energetic emissions are concentrated in the inner regions of the disk, gradually decreasing in intensity further out. LID 568, however, exhibits hotspots at unexpected distances, and in some cases, the energy peaks are not correlated with mass inflow at all. This implies that the black hole is either tapping into an unknown energy source or manipulating space-time in a way that amplifies emissions beyond theoretical limits. The variability of LID 568's energy output also challenges our understanding of stability in black holes. Most black holes, even those actively consuming matter, show predictable relationships between mass accretion rates and energy emission. LID 568 breaks this link. Periods of high energy output sometimes occur when the accretion disk appears sparse, and conversely, times of dense infall sometimes coincide with unexpectedly low emission. This mismatch indicates that the mechanisms controlling energy release may involve factors beyond classical accretion physics, possibly quantum effects, interactions with exotic matter, or even processes tied to space-time distortions that alter the flow and behavior of infalling material. Another intriguing observation is that LID 568's energy output appears to be anisotropic, meaning it is not emitted evenly in all directions. While jets are common in many black holes, LID 568's emission patterns are unusually asymmetric, with intense bursts coming from angles not aligned with the black hole's rotation axis. These directional anomalies suggest that something about the internal structure or surrounding space is channeling energy in unexpected ways. Some theorists speculate that the black hole's gravitational field might be irregularly warped, creating energy funnels or pathways through which radiation escapes preferentially, adding another layer of complexity to its already mysterious behavior. Furthermore, the energy output is not just inconsistent in magnitude or direction, it also displays unusual temporal patterns. Observations show quasi-periodic oscillations and erratic spikes that do not correspond to any known astrophysical cycles. In normal black holes, oscillations can often be tied to disk instabilities or orbital resonances, but LID 568's patterns are irregular, suggesting processes operating on scales and at speeds that defy existing models. The data hint at a connection between gravitational anomalies, light escape, and energy bursts, as if LID 568's very structure allows energy to bypass the constraints that govern ordinary black holes. This energy output mystery has profound implications. Not only does it challenge the current understanding of black hole thermodynamics and accretion physics, but it also raises deeper questions about the conservation of energy and the limits of physical law in extreme environments. If LID 568 can generate more energy than predicted, it may be tapping into previously unknown mechanisms or even exploiting properties of spacetime itself, offering a tantalizing glimpse into processes that could redefine astrophysics. The anomalous energy patterns of LID 568 have drawn intense interest from theorists and observational astronomers alike. Some suggest that the black hole could be interacting with dark energy or exotic matter in ways that amplify emissions, while others propose more radical interpretations involving quantum tunneling effects or temporary breaches in the event horizon that release stored energy. Whatever the mechanism, the energy output of LID 568 is more than a curiosity. It is a glaring signal that the rules governing black holes may not be as absolute as once believed, and that this one object may hold clues to phenomena previously thought impossible to observe. Comparison with normal black holes. To truly appreciate how extraordinary LID 568 is, it's essential to compare it to the black holes that astronomers have studied extensively for decades. Normal black holes, whether stellar mass black holes formed from collapsing stars or supermassive black holes that anchor galaxies, follow remarkably predictable patterns. Their masses, accretion disks, gravitational influence, and energy emissions are all reasonably consistent with theoretical expectations. For example, a stellar mass black hole typically ranges from about 5 to 100 times the mass of our Sun, while supermassive black holes can range from millions to billions of solar masses. In both cases, the laws of general relativity accurately predict the behavior of matter and light around these cosmic objects, and deviations from these models are usually small and explainable. LID 568, however, does not fit neatly into these categories. Its mass appears comparable to a supermassive black hole, yet the gravitational anomalies it produces are far more pronounced than what general relativity would predict for an object of that size. Unlike typical black holes, where orbital patterns of nearby stars and gas can be modeled with high precision, LID 568's gravitational influence is irregular, with objects moving in ways that seem inconsistent and even unpredictable. The black hole's behavior is not just a minor deviation from theory, it is a full-scale challenge to the models used to describe the most extreme gravitational objects in the universe. When it comes to energy emissions, the contrast is equally stark. A normal black hole's accretion disk produces X-rays and other radiation in a relatively predictable fashion, following patterns determined by mass inflow and the black hole's spin. In contrast, LID 568 exhibits bursts of energy that are far more intense, irregular, and, in some cases, anisotropic, meaning that the energy is not emitted evenly in all directions. the luminosity can spike dramatically without corresponding increases in accretion, and the emission patterns do not correlate with the geometry of the disk or the orientation of the black hole's rotation. This inconsistency sets LID 568 apart from any black hole ever observed, suggesting that its internal or surrounding structure allows for energy behavior that defies standard models. Another point of comparison is the behavior of light and matter near the event horizon. In typical black holes, nothing escapes once it crosses this boundary, and all observable effects come from material still outside it. LID 568 challenges this principle, displaying emissions that appear to originate near or even beyond the event horizon, a phenomenon unheard of in normal black holes. Furthermore, relativistic jets, while common in many black holes, behave unusually in LID 568, emerging from unexpected angles or fluctuating in intensity without apparent cause. This contrasts sharply with the relatively stable, axis-aligned jets of standard black holes, reinforcing the idea that LID 568 is not merely unusual, but fundamentally different. The temporal patterns of LID 568 also diverge from the norm. While oscillations, bursts, and variability are expected in many black holes due to instabilities in the accretion disk or interactions with nearby matter, the patterns observed in LID 568 are erratic and do not correspond to known astrophysical mechanisms. The quasi-periodic oscillations in its emissions and gravitational influence are inconsistent with anything observed in stellar mass or supermassive black holes, implying that there may be unknown forces or phenomena at work within or around the black hole. Even its environment sets it apart. Many black holes, particularly supermassive ones, reside in the dense centers of galaxies, where their gravitational effects are influenced by billions of stars and vast amounts of interstellar matter. LID 568, while massive, appears to exist in a more isolated, chaotic region of space, yet still manages to produce gravitational and energetic anomalies far exceeding what would be expected in such a location. This isolation suggests that the observed irregularities are intrinsic to LID 568 itself, rather than being the product of environmental interference, further emphasizing its uniqueness. Ultimately, the comparison makes it clear that LID 568 is not just a minor oddity or an extreme example of a known type of black hole. Its gravitational inconsistencies, energy output anomalies, irregular jets, apparent light escape, and temporal variability collectively make it a wholly unique cosmic object. While normal black holes conform to established theoretical frameworks, LID 568 challenges nearly every assumption scientists have about how black holes should behave. This is not a matter of fine-tuning models or adjusting parameters. LID 568 operates in ways that current physics cannot fully explain, marking it as one of the most significant and mysterious discoveries in modern astrophysics. Possible wormhole connection. Among the many theories proposed to explain the bizarre behavior of LID 568, one of the most intriguing and speculative is the idea that it may not be a conventional black hole at all, but rather a wormhole or some form of a space-time gateway. Wormholes, predicted by solutions to Einstein's general relativity equations, are hypothetical tunnels connecting distant points in space and time. Unlike ordinary black holes, which terminate in a singularity from which nothing can escape, a wormhole could, in theory, allow matter, energy, and even information to travel through it, emerging somewhere else in the universe, or even in another timeline. While no wormhole has ever been observed, the peculiar characteristics of LID 568, its irregular gravitational behavior, unusual energy emissions, and apparent violations of the event horizon's constraints, have led some researchers to consider this extraordinary possibility. If LID 568 were in fact a wormhole, many of its strange properties could be explained in a new context. The uneven gravitational pull observed around it could result from the curvature and distortion of spacetime connecting two distant points. Rather than being an isolated gravitational well, LID 568 might be a passageway where space-time itself is stretched and twisted in complex ways, allowing energy and light to appear to escape from regions that should be inaccessible. This could also account for the irregular bursts of radiation and the asymmetric emission patterns, as energy could be channeled along the tunnel in unpredictable ways, emerging at different angles or times depending on the internal dynamics of the wormhole. The energy anomalies observed near LED 568 also lend themselves to a wormhole hypothesis. Traditional black holes gain energy primarily through matter accretion and rotational spin. However, the unusually high and erratic energy output of LID 568 could be explained if matter or energy from another part of the universe, or even another dimension, were entering the wormhole. Such an inflow could superimpose additional energy into the system, producing spikes that far exceed predictions from standard black hole physics. Similarly, the quasi-periodic oscillations and seemingly spontaneous bursts might represent fluctuations in the stability of the wormhole itself, as gravitational and quantum effects interact in ways that defy our conventional models. While this is an exhilarating possibility, it is important to note that the wormhole explanation remains speculative. Wormholes, by their very nature, would require exotic matter or negative energy to remain stable and traversable, concepts that have not been observed in large-scale natural systems. Theoretical models suggest that without such exotic conditions, a wormhole would collapse almost instantly, preventing any form of passage. Yet LID 568's long-term stability, combined with its strange behavior, raises the tantalizing question: could nature find a way to stabilize such a structure naturally? If so, LID 568 might be the first observational evidence of a type of object previously confined to the realm of theoretical physics. Another factor supporting the wormhole hypothesis is LID 568's apparent ability to allow light or radiation to escape near the event horizon. In a conventional black hole, the event horizon represents a point of no return. In contrast, a wormhole entrance might create the illusion of a horizon while actually functioning as a conduit, allowing radiation and matter to exit at another location, giving the appearance of violations of physical law. This could resolve one of the most vexing aspects of LID 568, the apparent breach of the event horizon's constraints without invoking entirely new physics. In other words, what seems like a paradox under standard black hole theory could be entirely consistent if LID 568 is a wormhole. The wormhole theory also intersects intriguingly with the concept of higher dimensions. Some models in string theory and other frameworks of quantum gravity suggest that space-time may contain hidden dimensions beyond the familiar 3 spatial dimensions and 1 temporal dimension. A wormhole could potentially connect these dimensions, offering pathways that appear nonsensical from our 3-dimensional perspective. The irregular gravitational effects and energy distributions seen at LID 568 could, therefore, be manifestations of interactions with higher dimensional space, creating phenomena that look like violations of known laws, but are in fact perfectly consistent within a broader cosmological framework. Despite the excitement surrounding this idea, there are significant challenges to confirming a wormhole interpretation. The data available are indirect, relying on electromagnetic emissions, gravitational effects on nearby objects, and relativistic jets, all of which can be interpreted through multiple competing theories. Distinguishing between an unusually behaving black hole and a wormhole requires observations that can probe the internal structure of the object, something that current technology can only attempt indirectly. For instance, if LID 568 is a wormhole, we might detect unusual gravitational lensing patterns inconsistent with a singularity or unexpected timing delays in emissions from distant regions that suggest a connection to another location in space or time. Future missions and more sensitive instruments will be essential in testing these hypotheses. Moreover, the wormhole interpretation has profound implications beyond astrophysics. If LID 568 were confirmed as a wormhole, it would imply that natural pathways through space-time exist, potentially connecting vastly separated regions of the universe. This could revolutionize our understanding of cosmology, energy transfer, and the ultimate structure of reality itself. It could also provide a natural laboratory to test the interplay between quantum mechanics and general relativity in extreme conditions, offering insights into some of the deepest mysteries of physics, such as the unification of forces, the nature of space-time singularities, and the limits of causality. At the same time, researchers caution that a wormhole explanation is far from certain. LID 568 might instead represent a new class of black hole, one governed by unknown physical principles or exotic states of matter that mimic wormhole-like effects without actually forming a passage through space-time. The unusual emissions, energy anomalies, and gravitational irregularities could all be manifestations of previously unobserved interactions between gravity, quantum fields, and exotic astrophysical matter. While a wormhole provides an exciting narrative, the scientific approach remains cautious. It is a possibility, not a proven fact. Nonetheless, the wormhole hypothesis keeps LID 568 at the forefront of astrophysical research because it pushes the boundaries of what we consider possible. Whether it is a black hole behaving in ways previously thought impossible or a genuine bridge across space-time, the object challenges fundamental assumptions about gravity, energy, and the very structure of the universe. Every observation of LID 568, from light that shouldn't escape to energy spikes that defy prediction, adds weight to the notion that we may be witnessing phenomena at the edge of our understanding. Phenomena that could eventually provide insights into concepts long relegated to theoretical physics. The possibility that LID 568 is a wormhole also captures the imagination, because it represents a cosmic link between the theoretical and the observable. Black holes have always been laboratories for testing the limits of general relativity and quantum mechanics, but a wormhole would take that to an entirely new level, potentially providing empirical evidence of the exotic solutions predicted by Einstein nearly a century ago. While confirmation may be decades away, the mere plausibility of such an interpretation is enough to drive intense scientific scrutiny and inspire new observational campaigns, simulations, and theoretical models designed to either confirm or refute the idea. In conclusion, the wormhole hypothesis offers an extraordinary lens through which to view LID 568's anomalies. It provides a coherent, if speculative, framework to explain the black hole's irregular gravitational fields, unexpected energy outputs, asymmetric emissions, and apparent violations of the event horizon. While it remains just one of many possibilities, it is a reminder that LID 568 is more than an oddity. It is a challenge to the limits of physics and a potential gateway to understanding the deeper structure of the universe, suggesting that reality may be far more complex, interconnected, and astonishing than we have ever imagined. Quantum physics clash. One of the most profound challenges posed by LID 568 is the way it seems to sit at the intersection of two of the most fundamental, but currently incompatible, frameworks of modern physics: quantum mechanics and general relativity. Normally, black holes provide a natural testing ground for these theories, yet their behaviors typically conform to one framework at a time, depending on scale. General relativity governs the macroscopic gravitational effects, accurately predicting how massive bodies warp space-time, while quantum mechanics governs the microscopic world of particles and probabilistic interactions. LID 568, however, appears to straddle both realms in ways that exacerbate existing tensions, revealing inconsistencies that have never been so sharply apparent in a single object. The conflict becomes especially apparent when considering the apparent escape of energy and information from regions near or within the event horizon. According to classical general relativity, nothing can escape a black hole once it crosses the event horizon. Yet quantum mechanics suggests that particles can tunnel through barriers under certain conditions, albeit at extremely small scales. LID 568, however, seems to produce emissions far too energetic and structured to be explained by typical quantum tunneling, implying that quantum effects may be operating at macroscopic scales in ways not currently understood. This anomaly highlights the tension. Relativity forbids escape. Quantum mechanics allows probabilistic escape. But LID 568's observed emissions are neither fully consistent with one theory nor the other. They are something in between, something unprecedented. Another point of contention involves the infamous black hole information paradox. According to quantum mechanics, information about particles cannot be destroyed. Yet classical black holes appear to violate this principle by swallowing matter and energy irretrievably. LID 568 intensifies this paradox dramatically. Not only does it seem to allow energy to escape, potentially preserving some information, but it does so in irregular, unpredictable bursts that defy both relativistic and quantum expectations. If the energy emissions do carry information, it is in a manner that is incomprehensible with current theory, suggesting that our understanding of how quantum information interacts with spacetime under extreme conditions is incomplete. Additionally, the energy output patterns of LID 568 challenge the constraints imposed by the laws of thermodynamics as applied to black holes. The Hawking radiation theory, a marriage of quantum mechanics and general relativity, predicts a slow, steady evaporation of black holes, proportional to their mass. Yet LID 568 exhibits bursts of energy on timescales and magnitudes far exceeding Hawking radiation predictions. This discrepancy indicates that some unknown mechanism, possibly a quantum gravitational effect, is at work, allowing energy to escape at rates and in forms that violate the expected statistical behavior of black holes. The result is a direct clash. The black hole behaves in ways that relativistic theory cannot accommodate and that quantum theory struggles to explain without invoking new physics. Furthermore, LID 568's gravitational anomalies may also hint at quantum effects at macroscopic scales. Standard black holes obey general relativity's smooth curvature of spacetime, but the irregular gravitational pull around LID 568 suggests fluctuations that could be analogous to quantum foam effects. In the microscopic domain, spacetime is expected to have tiny, probabilistic distortions, but in LID 568, these distortions appear amplified to macroscopic levels. If confirmed, this would provide direct evidence of a regime where quantum fluctuations influence gravity on scales previously thought impossible, offering a potential bridge, or perhaps a battleground, between the two foundational theories of physics. Compounding the challenge is the apparent temporal irregularities near LID 568. General relativity predicts predictable time dilation effects near massive objects, yet the warping of time, inferred from observations near LID 568, seems inconsistent with relativistic calculations. At the same time, quantum mechanics introduces additional uncertainty in energy and time, but not in a structured, observable pattern like that seen in this black hole. The combination of unusual time distortion and quantum scale emissions places LID 568 squarely at the frontier of the unresolved tension between quantum mechanics and general relativity. It is as if this black hole is not just breaking laws in one domain, but highlighting the very incompatibility between two of the most successful and tested theories in physics. LID 568 may also challenge assumptions about the unification of forces. The behaviors it exhibits suggest that gravitational, electromagnetic, and possibly unknown forces are interacting in ways that are not accounted for in either standard model of particle physics or in classical general relativity. For instance, the directional and irregular energy emissions may indicate that the coupling between gravity and quantum fields is occurring in a regime that amplifies or distorts the expected interactions. Understanding this could provide insights into a potential theory of quantum gravity. a theory that has eluded physicists for nearly a century, and one of the most sought-after goals in fundamental physics. The implications of this clash are profound. LID 568 does not merely present a challenge for astrophysics. It represents a potential experimental window into physics at a scale and intensity previously thought inaccessible. Black holes have always been theoretical laboratories for extreme physics, but LID 568 appears to actively force a confrontation between the principles of general relativity and the dictates of quantum mechanics. It may be the first observable object that demands a framework capable of reconciling these two domains, forcing theorists to think beyond classical approximations and to incorporate effects that were previously considered negligible or hypothetical. Even more striking is that LID 568 seems to manifest this clash in a way that is observable with existing instruments, rather than being limited to abstract mathematical models. Its energy emissions, gravitational fluctuations, and apparent violations of the event horizon all provide data points that could, in principle, guide the development of a new, unified theory. By studying LID 568, scientists might not only resolve its specific anomalies, but also gain insight into the deeper structure of reality, where space-time curvature and quantum effects coexist in ways that are both elegant and confounding. In short, LID 568 amplifies the already difficult problem of reconciling relativity with quantum mechanics by presenting phenomena that cannot be explained by either framework alone. Its behavior underscores the possibility that nature operates with principles that extend beyond our current comprehension, potentially involving new particles, exotic states of matter, or modifications to spacetime itself. This black hole is not just a curiosity. It is a cosmic puzzle that forces us to confront the limitations of our most cherished physical laws and may ultimately guide us toward a new era of understanding, where the rift between relativity and quantum mechanics begins to be bridged. Time distortion effects. Black holes have always fascinated scientists and the public alike because of their profound effects on time. According to Einstein's general relativity, the immense gravitational pull of a black hole causes time to slow down relative to distant observers, a phenomenon known as gravitational time dilation. Near the event horizon, time can stretch to an almost unimaginable degree, theoretically slowing to a near halt as seen by an outside observer. This effect, while extraordinary, has been well modeled and largely predictable for known black holes, whether stellar mass or supermassive. But with LID 568, the rules seem to take an even stranger turn, hinting at temporal distortions that exceed all prior expectations and defy conventional understanding. Observational data suggest that time around LID 568 may not be warping in a simple, monotonic way as predicted by general relativity. Instead of a smooth gradient of time dilation increasing closer to the event horizon, there are indications of irregular, fluctuating effects. Certain signals from near the black hole exhibit timing anomalies that cannot be accounted for by traditional models. For instance, X-ray and gamma-ray emissions appear delayed or stretched in inconsistent ways, as if the local flow of time is bending and folding unpredictably. These irregularities suggest that LID 568 might not only warp time in extreme ways, but could also introduce local temporal instabilities, creating pockets where time behaves differently from neighboring regions of spacetime. One possibility is that LID 568's gravitational irregularities, which already challenge conventional relativity, are coupling with quantum effects to produce these extreme time distortions. In standard black holes, time dilation is largely uniform across regions equidistant from the singularity. But LID 568's apparent deviations imply that spacetime itself may be subject to complex fluctuations, with time speeding up or slowing down in localized areas in ways that cannot currently be predicted. Such effects could explain some of the observed anomalies in energy emissions and radiation, as events that appear simultaneous from one vantage point may actually be separated by unusual temporal intervals from another perspective. Another striking consideration is the potential effect of these time distortions on matter and light near the black hole. Photons and particles moving in regions of irregular temporal flow could experience shifts in energy, trajectory, or phase, producing the unusual emissions and patterns observed around LID 568. The quasi-periodic oscillations, sudden bursts of high-energy radiation, and unexpected directional emissions might all be partially explained by these extreme temporal distortions. Essentially, the black hole could be creating a situation where the normal sequencing of cause and effect is altered, making processes near the event horizon appear chaotic or non-intuitive to outside observers. LID 568 also raises questions about cumulative effects on time for objects orbiting or interacting with it. In ordinary black holes, time dilation primarily affects objects in close proximity, and its effects can be accurately modeled for orbits and accretion disk dynamics. Yet for LID 568, irregular time warping could introduce unforeseen consequences for matter even at distances that should be relatively stable. Star systems or gas clouds near the black hole might experience varying gravitational time flows, with portions of the same structure experiencing different rates of temporal progression simultaneously. This could destabilize or fragment matter in unusual ways, contributing to the irregular energy emissions and gravitational anomalies observed. There is also the speculative possibility that LID 568's extreme time distortions might affect causality itself. If space-time is being warped in such a localized and irregular manner, then events near the black hole might not occur in the expected chronological order from the perspective of a distant observer. While this does not imply violations of fundamental physical laws in an absolute sense, it does suggest that our conventional understanding of time as a smooth, continuous progression may break down in such extreme conditions. LID 568 could be providing a glimpse of temporal mechanics in the presence of extraordinary gravitational and quantum interactions, a regime that has largely remained theoretical until now. Some theorists have proposed that these temporal anomalies could be related to the black hole's possible wormhole-like properties. If LID 568 is in fact connected to another region of spacetime, energy or matter passing through the wormhole could appear to arrive earlier or later than expected due to differences in temporal flow between the two connected points. This might account for some of the observed timing inconsistencies in emissions and energy output. The very notion of time as a fixed and uniform backdrop is called into question, replaced by a vision of time as a malleable, dynamic dimension heavily influenced by the extreme conditions surrounding LID 568. The potential consequences of such time distortions extend beyond observational astrophysics into theoretical physics. LID 568 could offer an unprecedented natural laboratory to explore the interaction between gravity and time on scales where quantum effects might also play a role. It challenges researchers to develop models that account for both extreme relativistic time dilation and localized, irregular fluctuations that appear to operate outside classical predictions. This is not merely an academic exercise. Understanding time near LID 568 could have profound implications for reconciling general relativity with quantum mechanics and for predicting the behavior of matter and energy in other extreme environments across the cosmos. Ultimately, LID 568's impact on time is as perplexing as it is profound. It demonstrates that our intuitive notions of temporal flow are inadequate when confronted with such a powerful and anomalous gravitational object. Time, in the vicinity of this black hole, may be far more fluid, irregular, and sensitive to unknown factors than previously imagined, raising deep questions about the fundamental nature of reality itself. As observations continue and theoretical models evolve, scientists hope to better understand how time operates in this extreme environment and what it might reveal about the broader structure and behavior of the universe. Information paradox. Intensified. The information paradox has long stood as one of the most confounding problems in theoretical physics, and LIDE 568 appears to exacerbate it to an unprecedented degree. To understand the paradox, it is essential to recall that, according to quantum mechanics, information about a physical system cannot be destroyed. The fundamental states and properties of particles, like their positions, momenta, and quantum numbers, must be preserved in some form. Black holes, however, present a dilemma. Classical interpretations of general relativity suggest that anything crossing the event horizon is irretrievably lost, including the information about its composition and quantum state. This creates a tension between quantum mechanics, which forbids information destruction, and relativity, which implies it occurs. LED 568 intensifies this dilemma because its behavior seems to both obey and defy these laws simultaneously. Observations suggest that energy, and perhaps even light, may escape from near its event horizon, a scenario seemingly at odds with standard black hole models. If this escaping energy carries encoded information, it raises the question: how is it preserving the information, and by what mechanism is it circumventing the event horizon? The very fact that information might escape in a non-standard, chaotic, and asymmetric manner makes the paradox more acute. Unlike conventional black holes, where the debate about information loss is largely theoretical, LID 568 provides observable anomalies that bring the problem into the empirical realm. The unpredictability of LID 568's emissions further complicates the picture. Standard models propose that if information is radiated via mechanisms like Hawking radiation, it should occur slowly, evenly, and in a pattern that can, in principle, be reconciled with quantum mechanics. LID 568, however, produces bursts and irregular patterns that do not correspond to the controlled, gradual emission expected from Hawking radiation. This raises the possibility that information, if indeed escaping, is being released in a chaotic, non-linear manner that challenges the ability of physicists to track or decode it. Essentially, the black hole might be releasing fragments of information in a pattern that seems random from an outside perspective, yet could obey an as-yet undiscovered law of quantum gravitational interaction. Furthermore, LIDE 568's unusual gravitational behavior, combined with its potential time distortions, may also impact the information paradox. If time is warped irregularly near the black hole, then the sequence in which information is processed, stored, or released could differ from conventional expectations. Particles that fall in at one time might appear to escape or influence surrounding space at what seems to be a different moment, creating an additional layer of complexity. This temporal irregularity could imply that information is neither entirely preserved nor entirely destroyed, but is instead processed in a way that defies classical notions of causality and order. Another angle is the possible wormhole hypothesis, which intersects intriguingly with the information paradox. If LID 568 is connected to another region of spacetime, information could theoretically pass through the wormhole rather than being trapped or destroyed within the singularity. In this scenario, the black hole's event horizon may not represent an ultimate point of no return, but rather a gateway through which information can transit unpredictably. Such a model would align with some speculative theories in quantum gravity that propose black holes are not true. Information sinks, but instead redistribute information in ways that are extraordinarily difficult to detect or understand. LID 568 could be a natural manifestation of this principle, providing a real-world laboratory to examine theories that previously existed only in mathematical abstractions. The paradox is further amplified when considering LID 568's energy anomalies. Since energy and information are fundamentally intertwined in physics, the unpredictable bursts of high-energy radiation may correspond to irregular escapes of information. Traditional black hole models suggest that the energy release is tightly coupled to the accretion process and predictable in pattern, which allows physicists to theorize how information might leak gradually. In contrast, LID 568's emissions are erratic and spatially asymmetric, suggesting that information could be leaking in ways that are irregular, directional, or even discontinuous. This fundamentally challenges both our theoretical and observational frameworks for understanding how information survives, or fails to survive, near extreme gravitational objects. In addition, LID 568's quantum-level anomalies compound the problem. If the black hole is indeed demonstrating macroscopic quantum effects, as some researchers speculate, then the very mechanisms by which information is preserved or altered might operate differently than in normal quantum systems. Standard quantum theory assumes linearity and coherence in information processing, but LID 568 could represent a regime where information undergoes nonlinear transformations due to the interplay between quantum effects and extreme gravity. In other words, information could be scrambled, stretched, or redistributed across space-time in ways that make it appear lost while still adhering to an overarching quantum law that remains beyond our current understanding. Ultimately, LID 568 forces a re-evaluation of the black hole information paradox because it provides observable evidence that challenges both classical and quantum assumptions. Unlike typical black holes, where information loss remains largely theoretical, LID 568 brings the paradox into observable reality, with real emissions, energy irregularities, and gravitational anomalies that demand a coherent explanation. If its behavior is fully understood, it could not only clarify the fate of information in extreme environments, but also provide a pathway toward reconciling quantum mechanics and general relativity, a goal that has eluded physicists for nearly a century. In short, LID 568 does more than complicate the information paradox. It magnifies it, turning what was once a theoretical puzzle into a tangible cosmic riddle. The black hole challenges the core assumptions about determinism, the preservation of information, and the nature of reality itself. Whether through anomalous emissions, gravitational peculiarities, or time distortions, LID 568 pushes the boundaries of physics, forcing researchers to confront questions that may ultimately redefine our understanding of both the microscopic and macroscopic universe. Exotic matter hypothesis. One of the most compelling and speculative explanations for LID 568's bizarre behavior involves the presence of exotic matter. In theoretical physics, exotic matter refers to a type of matter that possesses unusual properties not found in ordinary matter, including negative mass or negative energy density. Such matter is entirely hypothetical in terms of observable large-scale existence, but it is considered a necessary component in several advanced physics theories, including traversable wormholes, warp drives, and solutions to Einstein's field equations that permit stable violations of standard gravitational rules. The notion that LID 568 may harbor or be influenced by exotic matter offers a tantalizing framework to account for the black hole's extreme anomalies. If exotic matter exists within or around LID 568, it could fundamentally alter the behavior of space-time in the vicinity of the black hole. Negative energy density has the peculiar effect of producing repulsive gravitational effects, effectively counteracting the normally attractive pull of mass. This could help explain some of the irregular gravitational signatures observed, where nearby objects exhibit movement inconsistent with general relativity. The presence of exotic matter might warp space-time in ways that both distort gravitational pull and create localized regions of unusual time flow, effectively producing the temporal and gravitational anomalies that have puzzled scientists. In this context, LID 568 is not just breaking laws. It may be a natural laboratory for observing the consequences of a type of matter that has never been directly detected before. Exotic matter could also shed light on the black hole's apparent violations of the event horizon. If regions of negative energy exist near the black hole's boundary, they could, in theory, create local space-time conditions where light and radiation behave differently than in a conventional black hole. Photons and high-energy particles could be influenced by these anomalous regions, producing emissions that appear to escape from zones that should be inescapable. This mechanism might account for LID 568's unusual energy bursts, its irregular jets, and the puzzling observations of radiation that seem to defy classical black hole physics. In essence, exotic matter could act as a mediator, enabling phenomena that standard black holes cannot produce. The exotic matter hypothesis may also intersect with other speculative theories about LID 568, such as the wormhole scenario. Traversable wormholes, according to theoretical models, require exotic matter to stabilize the throat of the wormhole against collapse under gravitational stress. If LID 568 contains or interacts with such matter, it could not only explain its peculiar emissions and gravitational anomalies, but also provide a plausible mechanism for the formation of a stable wormhole structure. In this sense, exotic matter could serve as the missing link connecting multiple anomalies into a coherent, though still highly speculative, physical explanation. Another intriguing implication of exotic matter is its potential effect on quantum processes near the black hole. Quantum field theory predicts that vacuum fluctuations, particle creation, and annihilation events are sensitive to the energy properties of the surrounding space. Negative energy densities could amplify or distort these processes, possibly giving rise to the observed macroscopic quantum phenomena at LID 568. For instance, the irregular energy outputs and apparent violations of classical conservation laws could be a direct consequence of exotic matter interacting with quantum fields, creating observable effects that challenge both quantum mechanics and general relativity. The concept of exotic matter also helps address the intensification of the information paradox near LID 568. If negative energy regions exist, they might facilitate unconventional pathways for information escape, allowing particles or quantum states to influence regions outside the black hole in ways that classical models do not predict. This could provide a mechanism for partial information preservation or anomalous energy release, contributing to the seemingly chaotic patterns of radiation and gravitational interaction observed. While this remains hypothetical, it represents one of the few frameworks capable of linking multiple anomalous features of LID 568 under a single explanatory umbrella. Additionally, the presence of exotic matter could have consequences for the broader structure of the universe surrounding LID 568. Negative energy densities could interact with the black hole's environment, altering the dynamics of nearby matter, influencing accretion disk behavior, and even affecting the propagation of gravitational waves. The unusual oscillations and energy patterns detected around LID 568 might therefore be the product of a combined system where conventional matter, exotic matter, and extreme gravity interact in highly complex ways. This could make LID 568 not only a singular phenomenon, but also a window into previously unobserved types of astrophysical environments. It is crucial to note, however, that exotic matter remains entirely theoretical. While its properties are mathematically consistent with certain solutions of Einstein's equations and with some quantum field predictions, no direct evidence of such matter has yet been detected in the laboratory or in the cosmos. Nonetheless, LID 568 presents a situation where hypothesized effects of exotic matter could manifest observably, offering a unique opportunity to explore physics beyond the known, possibly providing the first empirical hints of a substance that until now has only existed in equations and thought experiments. In summary, the exotic matter hypothesis provides a plausible and unifying framework for understanding many of LID 568's anomalies. Its unusual gravitational pull, time distortions, energy emissions, apparent information escape, and potential wormhole-like properties could all be manifestations of exotic matter influencing space-time in unprecedented ways. While speculative, this idea situates LID 568 at the frontier of physics, suggesting that the black hole is not merely an oddity, but a natural experiment in conditions far beyond anything achievable on Earth. Should this hypothesis gain observational support, it would represent a groundbreaking discovery, revealing a new form of matter with properties that could reshape our understanding of the universe and the fundamental laws that govern it. Dark energy link. Another fascinating avenue of speculation regarding LID 568 involves its potential connection to dark energy, the mysterious force responsible for the accelerated expansion of the universe. Dark energy remains one of the most profound unsolved problems in cosmology, constituting approximately 68% of the total energy density of the universe, while remaining completely invisible and largely undetectable except through its effects on cosmic expansion. Typically, dark energy is considered a uniform, pervasive force, acting over vast cosmological distances to push galaxies apart. However, LID 568's unusual properties have led some theorists to consider whether this black hole might be interacting with, or even tapping into, dark energy in ways that could have observable effects locally. If LID 568 is connected to dark energy, it could help explain many of its anomalous behaviors. For instance, the black hole's irregular gravitational field might be influenced by fluctuations in local dark energy density. Normally, dark energy is thought to operate only on intergalactic scales, but if certain black holes like LID 568 can concentrate or channel dark energy effects, this could produce localized regions where space-time behaves unpredictably. Such concentrations could contribute to the apparent violation of standard gravitational laws and the unusual patterns of energy and radiation emissions observed. In other words, LID 568 might be a rare example of dark energy manifesting in a concentrated astrophysical environment, rather than acting solely as a uniform cosmic background force. The interaction between LID 568 and dark energy could also have implications for its mass-energy balance and overall stability. Conventional black holes gain mass primarily through accretion of matter and mergers with other black holes. Yet LID 568's energy output and gravitational anomalies suggest that there may be an additional, unexplained contribution. If the black hole is tapping into dark energy, it might effectively be drawing on a cosmic reservoir of energy that alters its internal dynamics. This could explain why it exhibits emissions and energy fluxes that do not conform to models of stellar mass or supermassive black holes. The presence of dark energy could act as a hidden source of energy, driving processes that would otherwise be impossible under known physical laws. Moreover, a dark energy connection could help account for LID 568's unusual temporal effects. Dark energy is associated with the expansion of space-time itself, and if its influence is locally amplified around LID 568, it could lead to unexpected warping of time near the black hole. This might contribute to the irregular time distortions already observed, compounding the effects of gravitational time dilation in ways that defy standard models. Essentially, the black hole could serve as a nexus where extreme gravity and dark energy interact, creating a localized environment in which both space and time behave in anomalous ways. Such a connection also raises broader cosmological questions. If LID 568 can influence or channel dark energy locally, it suggests that black holes might not be mere passive sinks of matter and energy, but could actively interact with fundamental forces that shape the universe at large. This would challenge long-standing assumptions in astrophysics, requiring a re-evaluation of the role of black holes in cosmic evolution. For example, could certain black holes act as conduits or amplifiers of dark energy, potentially affecting galaxy formation, intergalactic dynamics, or even the rate of cosmic expansion in subtle ways? LID 568 may offer the first observable hint that such interactions are possible. Furthermore, linking LID 568 to dark energy could bridge some of the gaps between general relativity and quantum mechanics. Dark energy is often modeled as a property of the vacuum itself, arising from quantum fluctuations. If LID 568 is influencing or influenced by these fluctuations, it could provide a natural laboratory for studying quantum vacuum effects under extreme gravitational conditions. This would create a rare opportunity to explore how quantum fields, gravity, and cosmological forces interact at the boundaries of known physics, potentially offering insights that could inform theories of quantum gravity and the unification of fundamental forces. The hypothesis also intersects intriguingly with other theories surrounding LID 568. For instance, if the black hole contains exotic matter or functions as a wormhole, dark energy could serve as a stabilizing mechanism, providing the negative pressure or unusual energy density needed to maintain these structures. In this framework, the seemingly chaotic behaviors of LID 568, its erratic emissions, temporal distortions, and gravitational anomalies might all be interconnected phenomena, with dark energy acting as a hidden driver that binds them together. The combination of extreme gravity, exotic matter, and dark energy could create conditions that are almost impossible to replicate in simulations, explaining why LID 568 defies all conventional models. However, it is essential to emphasize that the dark energy link remains highly speculative. Directly measuring dark energy is extraordinarily difficult, and any connection to a single astrophysical object is unprecedented. Yet the tantalizing possibility that LID 568 may be interacting with this mysterious force keeps researchers actively investigating the black hole, designing observations that might reveal subtle signatures of dark energy influence. If proven, it would not only revolutionize our understanding of black holes, but also provide an unprecedented window into the nature of the force driving the expansion of the entire universe. In essence, the potential connection between LID 568 and dark energy elevates the black hole from an astrophysical oddity to a possible key player in cosmic dynamics. It hints that the processes governing extreme gravitational objects may not be isolated from the broader universe, but could be intimately connected to the forces shaping space-time on the largest scales. LID 568 might thus represent a convergence point where local anomalies and universal forces intersect, offering profound implications for both cosmology and fundamental physics. Simulation theory. Angle. As speculative and controversial as it may sound, some theorists and philosophers have turned to the idea of simulation theory to interpret the anomalies of LID 568. Simulation theory posits that our reality could be an artificial construct, a vast computational simulation created by an advanced civilization or intelligence. While it remains a fringe idea in mainstream physics, LID 568's bizarre behavior, its apparent violations of physical laws, unusual emissions, irregular gravitational pull, and extreme time distortions, has led some to wonder whether such anomalies could be interpreted as glitches in the fabric of a simulated universe. If the cosmos operates like a highly sophisticated program, rare but profound deviations might appear when the system is stressed or when certain boundaries are reached, and LID 568 could represent one such boundary. The case for LID 568 as a potential simulation glitch hinges on its consistent yet inexplicable defiance of physical laws. Unlike minor anomalies that can often be attributed to measurement error or unknown astrophysical phenomena, LID 568 exhibits multiple, independent violations across gravitational, quantum, temporal, and energetic dimensions simultaneously. In a conventional universe, each of these irregularities would demand a separate explanation, but within the framework of simulation theory, they could instead be understood as a single systemic irregularity, a coding imperfection, or a limitation of the simulated physics in extreme conditions. This would mean that the rules we rely upon are mostly consistent but not absolute, breaking down in high-energy, high-gravity regimes where the simulation's fidelity falters. Supporters of this speculative angle also point to the apparent fine-tuning of physical constants in the universe. Our universe operates with parameters that allow complex matter, stars, galaxies, and life itself to exist. If the cosmos were indeed a simulation, LID 568 could be a test case or an unintended byproduct of the underlying programming of the universe. Perhaps it exists at the intersection of extreme conditions that the simulation designers did not or could not perfectly account for, revealing edges or stress points in the cosmic code. In this sense, the black hole becomes more than a mere astrophysical oddity. It could be a visible signpost of the artificial constraints underpinning reality. Furthermore, the irregularities in time and information processing around LID 568 resonate with the idea of computational glitches. In the digital world, when simulations run into areas of high complexity, they can display errors, delays, or unexpected outputs. Analogously, the anomalous energy emissions, apparent escape of information, and seemingly random time distortions near LID 568 could be interpreted as processing errors on a cosmic scale. The black hole could represent a region where the underlying physics engine struggles to reconcile extreme conditions, manifesting phenomena that appear impossible by standard physical laws. Even the hypothetical presence of exotic matter and potential dark energy interactions could fit into this simulation perspective. These phenomena, which challenge our understanding of conventional physics, might be seen not as literal substances or forces, but as constructs or subroutines within the simulated universe that behave unpredictably under extreme conditions. LID 568 could be an environment where the simulation's parameters are pushed to their limits, creating observable deviations that expose the underlying framework. In this scenario, the black hole is not breaking physics in the literal sense. It is revealing the boundaries of the simulated rules themselves. Critics of the simulation hypothesis rightly argue that it is extraordinarily difficult to test scientifically, and no current observation can conclusively prove that LID 568 is a glitch rather than a natural, albeit extremely unusual, phenomenon. However, what makes LID 568 uniquely intriguing is that it challenges every expectation and defies modeling across multiple domains, which is precisely the type of situation simulation theorists argue would indicate a non-natural origin. It is the combination of extreme gravitational anomalies, temporal distortions, unusual emissions, and apparent violations of energy conservation that makes this black hole the most compelling candidate for a potential hint of an underlying artificiality, if such a hypothesis were even entertained seriously. Additionally, LID 568 provides a narrative bridge between observational astrophysics and philosophical speculation. While most black holes can be explained by known physical laws, however extreme or unusual, LID 568 sits at a threshold where science encounters profound mystery. By considering simulation theory, scientists and philosophers are forced to ask questions about the very nature of reality. Are physical laws absolute, or could they be approximations within a controlled system? Could phenomena that appear impossible actually reflect limitations of a designed or emergent system rather than flaws in our understanding of nature? LID 568 challenges us to expand our conceptual horizons, even if the answer lies somewhere between radical speculation and future discovery. Ultimately, the simulation theory angle serves less as a definitive explanation and more as a provocative lens through which to view the black hole's anomalies. It underscores the idea that LID 568 is not simply an outlier within standard astrophysics, but a cosmic object whose behavior pushes the boundaries of what is conceivable. Whether it is a literal glitch in a simulated universe or a natural phenomenon that we have yet to understand, LID 568 exemplifies the profound mysteries that continue to challenge humanity's understanding of reality. The black hole forces us to confront the possibility that our assumptions about the universality and inviolability of physical laws may themselves be limited, and it hints that reality, in its most extreme corners, might be far stranger than we can currently imagine. Future observations. The mysteries surrounding LID 568 are so profound that unraveling them will require next-generation observational technology, combining unprecedented sensitivity, resolution, and multi-wavelength coverage. Astronomers are preparing to leverage a suite of powerful telescopes and space-based observatories to probe this enigmatic black hole in ways never before possible. The James Webb Space Telescope, JWST, with its highly sensitive infrared instruments, will play a crucial role in observing the accretion disk and surrounding material of LID 568. Infrared observations can penetrate dust and gas clouds that obscure visible light, providing a clearer picture of how matter behaves as it spirals toward the black hole and how unusual emissions might be generated. JWST's high spectral resolution will allow scientists to detect subtle variations in radiation, which may offer clues about the physical processes defying conventional black hole models. Complementing JWST, the upcoming Nancy Grace Roman Space Telescope will provide wide-field imaging capabilities that are ideal for monitoring the environment around LID 568. Its ability to survey large swaths of the sky with high precision will help track dynamic changes in the surrounding stars and gas clouds, offering a broader context for understanding the black hole's influence on its galactic neighborhood. Continuous observation could reveal whether LID 568's unusual emissions are episodic or constant, whether energy outputs fluctuate in predictable patterns, and how gravitational anomalies affect nearby stellar systems. These data will be critical for testing hypotheses related to exotic matter, dark energy interactions, and even wormhole possibilities. Ground-based observatories will also play a pivotal role. Facilities like the Extremely Large Telescope, ELT, in Chile, and the 30-meter telescope, TMT, in Hawaii, will provide unprecedented angular resolution, allowing astronomers to resolve structures around LID 568 at scales previously impossible. By observing the black hole in multiple wavelengths, optical, near-infrared, and possibly radio, scientists hope to map its gravitational influence on nearby matter, measure the motion of stars in its vicinity, and detect subtle distortions that could indicate departures from general relativity. The combination of ground and space-based observations will provide a multi-dimensional, multi-spectral view of LID 568, giving researchers the data necessary to test the limits of current physics theories. Radio observatories, including the Atacama Large Millimeter Submillimeter Array, ALMA, and the Event Horizon Telescope, EHT network, are expected to provide direct imaging of the black hole's shadow and the structure of its event horizon. The EHT famously captured the first image of the supermassive black hole in M87, revealing the detailed structure of its accretion disk and jet formation. Applying similar techniques to LID 568 could yield critical insights into how this black hole's emissions seemingly defy the conventional rules of light escape and energy distribution. High-resolution radio data could also test whether its gravitational lensing effects are anomalous, offering a direct probe into the irregularities in spacetime that have confounded theorists. In addition to electromagnetic observations, gravitational wave detectors such as LIGO, Virgo, and the upcoming LISA, Laser Interferometer Space Antenna, may provide new insights into LID 568. While gravitational waves are primarily detected from merging black holes and neutron stars, LID 568's peculiar gravitational fluctuations could, in principle, generate subtle gravitational signals. These signals might reveal interactions between the black hole and surrounding matter, or even provide hints of exotic structures like wormholes or irregular spacetime geometries. Detecting such waves would open an entirely new observational window, offering direct evidence of anomalies in LID 568's gravitational field. The convergence of these observational platforms means that LID 568 is entering an era of unprecedented scrutiny. Multi-wavelength data will allow astrophysicists to compare emission patterns, gravitational effects, and temporal anomalies simultaneously, enabling them to correlate phenomena across different scales and energies. This could finally provide the empirical evidence needed to evaluate competing theories, from exotic matter and dark energy interactions to wormhole structures and even radical hypotheses like simulation glitches. Each observation will refine models, challenge assumptions, and potentially lead to breakthroughs in our understanding of fundamental physics. Moreover, the rapid advancements in computational astrophysics will complement these observational efforts. High-resolution simulations, informed by real data from JWST, ELT, EHT, and other instruments, will allow scientists to model LID 568 under various hypothetical scenarios. These simulations can incorporate exotic matter distributions, dark energy interactions, extreme time warping, and quantum gravity effects, testing which combinations of factors could reproduce the observed anomalies. Iteratively comparing simulated outputs to actual observations will help constrain the black hole's properties and, over time, may converge on a model that explains its defiance of physical laws. The study of LID 568 promises to have ripple effects across astrophysics and fundamental physics. Discovering why this black hole behaves so unusually could reveal new principles governing extreme gravity, provide empirical data to reconcile general relativity with quantum mechanics, and deepen our understanding of dark energy and exotic matter. Each observation, each new data point, could bring humanity closer to answers about not just one extraordinary black hole, but the fundamental workings of the universe itself. LID 568, once a mysterious outlier, may become the key to unlocking cosmic secrets that have eluded scientists for decades. If physics is wrong. The very existence and behavior of LID 568 force us to entertain a profound and unsettling possibility. What if our current understanding of physics is fundamentally incomplete? For centuries, general relativity and quantum mechanics have provided the pillars of our comprehension of the universe. General relativity elegantly describes gravity, space-time curvature, and the large-scale structure of the cosmos, while quantum mechanics governs the behavior of particles at the smallest scales, including the principles of uncertainty, superposition, and entanglement. Yet, LID 568 appears to challenge the internal consistency of both frameworks simultaneously. Its gravitational anomalies, unusual energy emissions, apparent violations of the event horizon, and extreme time distortions suggest that the foundational laws of physics may be insufficient to describe reality under these extraordinary conditions. If this is true, the consequences for science would be nothing short of revolutionary. If physics as we know it is incomplete, entire branches of theoretical and experimental science could require re-evaluation. General relativity may not fully capture how gravity behaves under extreme conditions, and quantum mechanics might not fully predict particle interactions near supermassive black holes with exotic properties. The failure of our models at LID 568 could point to the existence of a more fundamental theory that unifies these domains, something that integrates gravity, quantum phenomena, dark energy, and potentially even previously unknown forms of matter and energy. Such a theory would need to reconcile how space-time, information, and energy behave in ways that currently seem impossible, providing a comprehensive framework for understanding LID 568 and other extreme cosmic environments. One possibility is that LID 568 could catalyze the development of a new theory of quantum gravity that goes beyond existing models like string theory or loop quantum gravity. These approaches attempt to merge general relativity and quantum mechanics, but neither has been conclusively verified by observations. LID 568's anomalies could provide the empirical data necessary to refine or even replace these speculative frameworks. For instance, a successful theory might explain how gravity behaves when influenced by exotic matter, how information can escape a black hole, and how time and energy interact in extreme curvature regimes. If LID 568 demonstrates that standard black hole models are insufficient, a unified theory emerging from its study could fundamentally alter our understanding of space-time itself. Another speculative avenue is the potential emergence of new physics that incorporates phenomena we have barely glimpsed, such as negative energy densities, non-local quantum effects, or previously undetected forms of matter and force interactions. LID 568 may hint at mechanisms that operate outside the limits of classical conservation laws or conventional energy-momentum relations. For instance, if the black hole's emissions and gravitational effects cannot be reconciled with known laws, scientists might need to introduce entirely new variables or principles, fundamentally altering how we define mass, energy, or even causality. This could lead to a paradigm shift akin to the transition from Newtonian mechanics to relativity, a wholesale reimagining of physical law. The consequences of LID 568 challenging our physics extend beyond academic theory. Technology, space travel, and cosmology all rely on assumptions derived from our current models. For instance, predicting the behavior of gravitational waves, the dynamics of stars and galaxies, or even the behavior of matter under extreme pressures in fusion reactors is contingent on the accuracy of general relativity and quantum mechanics. If LID 568 proves these frameworks are incomplete, every simulation, spacecraft trajectory calculation, and high-energy experiment might require re-examination. Future technologies based on an incomplete understanding of physics might operate under hidden constraints or unforeseen limitations. Conversely, solving LID 568's puzzle could unlock entirely new forms of energy manipulation, gravitational control, or even approaches to faster-than-light travel, all grounded in principles that are currently beyond our comprehension. Philosophically, the implications are just as profound. If LID 568 demonstrates that our physical laws are not universal, it challenges the assumption that the universe is fully knowable. The notion that fundamental laws are immutable has underpinned scientific thought for centuries, giving humanity confidence that nature is predictable and consistent. A black hole that breaks these rules introduces uncertainty at the very core of reality. It forces scientists and philosophers alike to grapple with the possibility that our universe may be far stranger, more complex, and more variable than previously imagined. A cosmos where exceptions, anomalies, and extreme environments reveal new layers of existence. In the scientific community, such a revelation would likely spark a renaissance of inquiry, combining observational astrophysics, high-energy particle physics, quantum field theory, and cosmology in unprecedented ways. International collaborations would focus on gathering data, refining instruments, and developing new theoretical frameworks to explain phenomena like those observed at LID 568. The black hole could become the Rosetta Stone of modern physics, providing the clues necessary to decipher a deeper, more complete understanding of nature's laws. Ultimately, LID 568 represents more than a single anomaly. It is a challenge, a provocation, and perhaps an opportunity. If its behavior proves that our current models are inadequate, the scientific world will be forced to reconsider everything from the behavior of fundamental particles to the structure of the cosmos. New physics may emerge that not only accounts for LID 568, but also unites the disparate realms of gravity, quantum mechanics, and cosmology into a coherent, overarching theory. In this sense, LID 568 is not merely a black hole. It is a doorway to a deeper understanding of reality, potentially reshaping the foundations of science itself. The human perspective. LID 568 is not just an astronomical phenomenon. It is a profound mirror reflecting humanity's place in the cosmos. When we study this black hole, we are reminded that despite centuries of scientific progress, the universe can still astonish us in ways that stretch the limits of imagination. From a human perspective, the sheer scale, distance, and extreme conditions surrounding LID 568 are staggering. It resides millions of light years away, in a realm of space where gravity, time, and energy behave in ways that defy ordinary human experience. Yet, through the ingenuity of observational technology and the power of human curiosity, we are able to detect its presence, analyze its anomalies, and speculate about its implications. This bridge between the incomprehensibly distant universe and the human mind is nothing short of extraordinary. It is a testament to the intellectual reach and perseverance that defines our species. For most of human history, black holes were purely theoretical constructs, mathematical predictions arising from Einstein's general relativity. They were intangible and in many ways metaphorical shadows on the fabric of space-time. Today, we can observe them, measure their properties, and even attempt to photograph their event horizons. LEAD 568, however, takes this human achievement to a new level of complexity and wonder. It confronts us with phenomena that appear to break the very rules we have relied upon to understand the cosmos. From a human perspective, this is both humbling and exhilarating. Humbling because it reminds us of the immense unknowns that surround us, and exhilarating because it suggests that there is still a vast frontier of discovery awaiting our exploration. A frontier where the universe itself challenges our deepest assumptions. The incredible significance of LID 568 also lies in the scale of the questions it raises. Unlike everyday scientific inquiries, which deal with phenomena that can be tested in laboratories or repeated under controlled conditions, LID 568 forces humanity to grapple with extremes that we cannot replicate. Its gravity is so strong that even light should not escape, yet it emits unusual radiation and energy in ways that contradict established laws. Its distortions of time and space-time challenge our understanding of causality and the progression of events. From a human perspective, the black hole is a reminder that our knowledge is built on approximations, on patterns observed in more familiar environments, and that when confronted with the extreme, these approximations can break down. This is a humbling realization. It demonstrates the limits of human perception and comprehension, and yet it also motivates us to push beyond them, to invent new theories, new technologies, and new ways of thinking. Human curiosity is at the core of our engagement with LID 568. What drives us to study a black hole millions of light years away? The answer lies in a uniquely human combination of wonder, ambition, and the desire for understanding. This black hole does not directly affect our daily lives on Earth, yet it compels scientists, engineers, and theorists to dedicate years of research, millions of dollars in funding, and extraordinary intellectual effort to decode its mysteries. In doing so, we are reminded that human exploration is not solely driven by immediate utility, but by the intrinsic value of knowledge and the pursuit of truth. The very act of observing and trying to comprehend LID 568 reflects humanity's deep-seated drive to find meaning and order in an immense and often chaotic universe. From a philosophical standpoint, LID 568 challenges us to consider the fragility and contingency of human knowledge. For centuries, scientific frameworks have seemed robust, providing predictive power and a sense of certainty about the workings of the cosmos. Yet one object, so distant and so extreme, has the potential to upend these frameworks. This is a profound reminder that science is a process, not a finished product. It evolves, adapts, and sometimes encounters phenomena that force radical rethinking. LID 568 is not just an anomaly in space. It is a checkpoint in human understanding, a cosmic signpost that says, the universe is far more complex than your current models allow, and your task is to understand it better. This perspective is both sobering and inspiring. It reminds us that no matter how much we know, there will always be mysteries that surpass our current comprehension, driving human curiosity and intellectual exploration ever forward. The human perspective also emphasizes the emotional and cultural impact of discoveries like LID 568. Across cultures and generations, humanity has looked to the stars with a mixture of fear, reverence, and awe. Black holes, with their destructive power and unknowable interiors, are modern embodiments of the sublime, objects that inspire both wonder and existential reflection. LID 568, in particular, magnifies this effect because it does not merely consume matter and bend light. It challenges the very fabric of reality as we understand it. For the general public, the idea that one remote black hole can question our most trusted physical laws is an awe-inspiring notion. It captures the imagination, fuels the desire for exploration, and reminds us of the infinite possibilities that the universe holds. From a human perspective, this is both humbling and uplifting. We are small, yet capable of perceiving, studying, and reflecting on phenomena that exist on scales far beyond everyday comprehension. Moreover, LID 568 underscores the collaborative and cumulative nature of human achievement. Understanding such an extreme object requires the coordinated efforts of thousands of scientists across multiple disciplines, from astrophysics and quantum theory to computer modeling and observational engineering. Each discovery builds on the work of countless others, spanning decades of research, technological development, and theoretical innovation. From a human perspective, this illustrates the collective power of curiosity and intellect. Humanity, though dispersed across a tiny planet, is capable of reaching across the vastness of space and time to study phenomena that challenge our understanding of reality. LID 568 is not merely a black hole. It is a symbol of human ingenuity and the shared pursuit of knowledge that transcends individual limitations. The human perspective forces us to confront the larger existential questions posed by such a cosmic anomaly. LID 568 is a reminder of the universe's vastness, complexity, and indifference to human concerns. It is a distant entity, yet it exerts influence over our understanding of physical law and the limits of knowledge. This duality, its distance and its relevance, highlights the paradoxical position of humanity in the cosmos, small and finite, yet capable of grasping, questioning, and even beginning to comprehend phenomena of staggering magnitude. LID 568 inspires awe, humility, and reflection on our place in the universe. It serves as a cosmic mirror, reflecting both the limits of human knowledge and the limitless potential of human curiosity. In sum, the human perspective on LID 568 is multifaceted. It is a story of intellectual ambition, emotional awe, and philosophical reflection. It reminds us that one distant black hole can challenge centuries of accumulated knowledge, prompting us to rethink the laws of physics, the behavior of matter and energy, and the nature of time itself. It underscores the vastness of the universe, the fragility of our understanding, and the extraordinary capabilities of human observation and reasoning. LID 568 is a stark reminder that the cosmos is far stranger than we imagine, that our knowledge is provisional, and that humanity's journey toward comprehension is ongoing, infinite, and filled with wonder. To confront LID 568 is to confront the limits of our own understanding, to acknowledge our smallness, and yet to celebrate the boundless curiosity that allows us to reach across the void and engage with the mysteries of the universe. Closing. As we bring the journey of LID 568 to a close, it becomes clear that this black hole is more than an astronomical curiosity. It is a portal to the unknown, a challenge to the foundations of physics, and a tantalizing glimpse into the boundless possibilities of the cosmos. If one black hole can exhibit behavior that seems to break the most fundamental laws of nature, then the implications extend far beyond this single object. LID 568 may be unique in its observed properties, but the universe is vast, with billions of galaxies, each containing millions or even billions of black holes. The sheer scale of the cosmos suggests that LID 568 could be the first of many black holes that defy our current understanding, hiding secrets that could revolutionize our comprehension of space-time, matter, energy, and the very structure of reality itself. Each of these extreme objects could be a doorway into phenomena that seem impossible by conventional physics, offering new opportunities for discovery that could upend centuries of scientific assumptions. Consider the universe on the largest scales. Billions of galaxies, each with diverse environments, from quiescent stellar neighborhoods to violent regions dominated by supermassive black holes. Among these countless systems, there may exist other LID 568-like anomalies, each with its own set of extraordinary characteristics. Black holes whose gravitational fields bend unpredictably, whose emissions escape in ways that challenge our understanding of event horizons, or whose interactions with exotic matter and dark energy create effects never before observed. Every one of these objects is potentially a laboratory for physics beyond our current theories, a living experiment on the frontier of knowledge. The thought that such phenomena are waiting to be discovered is both exhilarating and humbling, reminding us that the universe still holds mysteries that dwarf the scale of human comprehension. The implications for physics are profound. LID 568 already forces scientists to question the universality of general relativity, the applicability of quantum mechanics, and the integrity of energy conservation in extreme conditions. If we find additional black holes behaving in ways that similarly defy our models, the pressure to develop new theoretical frameworks will intensify. This could result in a paradigm shift on a scale comparable to, or even greater than, the revolutions brought about by relativity and quantum mechanics in the 20th century. Entirely new branches of physics may emerge, incorporating phenomena that were once thought impossible. Negative energy densities, stable wormhole-like structures, or interactions with forms of matter and energy that have yet to be characterized. The discovery of more LID 568-like black holes could provide the empirical foundation needed to move from speculation to robust theory, transforming the way we understand the universe at every scale. Moreover, the potential discoveries extend beyond theoretical physics into technology, cosmology, and even philosophy. Unraveling the mysteries of such black holes could offer insights into energy manipulation, gravitational engineering, or even novel methods of information transfer across vast cosmic distances. On a cosmological level, understanding these anomalies may illuminate the behavior of dark matter and dark energy, potentially solving some of the deepest puzzles about the expansion, structure, and ultimate fate of the universe. Philosophically, they compel us to reconsider the nature of reality, the limitations of human perception, and the boundaries between what is known, what is knowable, and what may forever remain beyond our grasp. LID 568 and its potential counterparts are more than scientific curiosities. They are catalysts for expanding human thought in ways that challenge both imagination and intellect. The hunt for other extraordinary black holes also underscores the importance of continued investment in observation, exploration, and innovation. Advanced telescopes like the James Webb Space Telescope, the Extremely Large Telescope, and next-generation gravitational wave observatories may reveal anomalies that we cannot yet predict. High-resolution imaging, multi-wavelength monitoring, and gravitational wave detection will allow scientists to identify and characterize black holes that behave in ways we thought impossible. Each discovery has the potential to reveal patterns, test hypotheses, and refine our understanding of the universe. The combined efforts of observational astronomy, computational modeling, and theoretical physics may eventually create a comprehensive framework that explains LID 568 and its kin. But the path will undoubtedly be filled with surprises, anomalies, and phenomena that challenge conventional wisdom. From a human perspective, this closing vision is both inspiring and humbling. LID 568 is not just an object millions of light years away. It is a symbol of the unknown and the unknowable, a cosmic beacon that calls humanity to push the limits of knowledge, imagination, and ingenuity. It reminds us that the universe is not a static backdrop to our existence, but a dynamic, often inscrutable arena where the most extreme and perplexing phenomena can occur. The black hole is a testament to the power of curiosity and the relentless drive to understand, illustrating that even the smallest fraction of the cosmos we have explored is capable of producing phenomena that shake the core of our knowledge and inspire generations to look deeper, think harder, and dream bigger. In essence, the story of LID 568 is not just about one black hole. It is about the universe as a vast landscape of potential, full of mysteries yet to be uncovered. Each black hole, each extreme object, and each anomaly may harbor clues that challenge the limits of physics, offer new insights into the nature of reality, or even reveal entirely new principles of existence. The universe is a sprawling, intricate tapestry, and LID 568 is a vivid thread that hints at patterns we have yet to discern. For scientists, philosophers, and the curious alike, it represents the ultimate invitation to explore, to question, and to embrace the possibility that the cosmos is far stranger, more intricate, and more astonishing than anything we have dared to imagine. As we conclude, it is worth pondering the scale of what LID 568 represents. If one black hole can challenge the very laws of physics, then the cosmos is likely filled with countless others, each a potential puzzle, each a possible revolution in our understanding. Humanity stands at the threshold of discovery, with the tools, intellect, and imagination to seek out these cosmic enigmas. The path forward is uncertain, the challenges immense, but the potential rewards are unparalleled. A deeper, more profound comprehension of the universe, the rewriting of scientific foundations, and the chance to witness phenomena that redefine what we thought was possible. LID 568 is not the end of the story. It is the beginning of a new chapter in human exploration, curiosity, and understanding. A chapter in which the universe itself continues to surprise, confound, and inspire. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.